Happy Pi Day! This year I want to start the tradition of calculating the famous constant pi. This year we're going to do it using Python and random numbers. The method I'm using is from Matt Parker's Stand Up Maths channel, link in the description. So here's how it works. We're going to generate a pair of random numbers a and b. Then we'll see if they're coprime. Coprime numbers have 1 as their greatest common factor. We'll repeat this multiple times and keep track of how many pairs are coprime and how many are not. Now, given this information, here's how we'll calculate pi. It turns out that the probability of any two random numbers being coprime is 6 divided by pi squared. So, if we divide the number of coprime pairs that we get divided by the number of pairs, we're going to get 6 divided by pi squared. And then we can solve this and get pi. Now, let's see how we actually do this in Python. So in Python, we have to have a lower and an upper bound to generate random numbers. So I'm going to use 1 as my lower bound and 100 as my upper bound. We'll use a module called random to generate 1,000 pairs of random numbers. Then we'll create a function to check whether they are coprime. Now, the easiest way to do this is to get the factors of each number and check them. Then we'll check if the two random numbers we have generated have common factors apart from 1. If they do, we'll return false, they're not coprime. If they don't, we'll return true, that is, they are coprime. Finally, we store each pair of coprimes in a list. Now, since we'll be looping this whole process a fixed number of times, I will just store the index of the iteration in the coprimes list. That is, if the first pair of random numbers generated is coprime, we'll store the number 0 in the coprimes list. Then if the second pair also happens to be coprime, we'll add the index 1 and so on. Now, given this information, we are ready to calculate pi. Now, to do this, we'll have to use the length of the coprimes list, which is the number of coprime pairs in the whole 1,000 iterations that we generated. We'll take that length and we'll divide it by 1,000, and that'll give us the proportion 6 divided by pi squared. We can manipulate this equation and solve for pi. Alright, now let's actually write some code to do this. Okay, so we're going to start off by importing the random module. As I said, this is a module which will help generate random integers between a lower bound and an upper bound. But before we get started with that, we'll actually define the function to check whether two numbers are coprime. So we're going to say define is coprime, and we'll take in two numbers, a and b, as parameters. Now, to check if they're coprime, we want to get their factors. So a factors is get factors of a, and b factors is get factors of b. So I'm going to consider a factors and b factors as lists, where all the factors of the number, including the number of itself, are present, excluding one. And we have to define this function, get factors. So let's do that. So define get factors, and we're going to take in the parameter number. Okay, now we want to iterate through each number from 2 to the number itself, and check if any of those numbers is divisible by the number. So okay, here's what I'm talking about, right? So for I in range, we want to start at 2 and we want to go to number all the way up to the number, but we want to go all the way up to number plus 1 so that number itself is included. Okay, so here's what I'm talking about. So if I say number is 5, I want the for loop to include the 5, um, and the way to do that is just to add 1 at the ending point. Okay, so for I in range 2 to number plus 1, now we want to check if that number I is divisible by number. So the way we do that is take the remainder. So if number mod I, that's the modulus remainder, is 0, well, that means it's divisible, right? We want to add it to a factors list. So I haven't declared that up here, so let's do that quickly. Factors list is a blank list for now. So if we do get a number which is divisible, then we want to add it to the factors list. So factors list dot append I, and that's it. We can return the factors list. Okay, so we got our get factors function ready. Let's quickly test it out. So I'm going to say get factors of 4. So real quick, we'd expect a list with the numbers 2 and 4 to show up over here. Let's actually print it out so that we can see the output. We'll not see 1, we only expect to see a list containing the numbers 2 and 4. So let's see if it works. And indeed, that's what we see. All right, so our get factors function works. Now we know we can use it in our isCoprime function. We want to iterate through each factor in the factors list, right? So if you so we're going to say for a factor in a factors, and then we want to check if any one element is in the list of the other elements factors. So what I'm saying is this: if a factor is in B factors, right? Well, that means they're not coprime, right? So we're gonna declare a boolean here called coprime, and we're gonna initialize it to false, right? So if any one element in one numbers factor list is there in another numbers factor list, that means they're not coprime. So we're gonna set coprime to false. But if that is not the case, then we are going to set coprime to true. And another thing we need to keep in mind is if at all we find any common element between the factor list of the two random numbers that we generated, where we just want to break out of the loop because we immediately know that they're not coprime. So we just say break. Okay. Lastly, we can just return coprime. Okay. Now let's test if this function works. So I'm going to say print is coprime. Let's pick two numbers 3 and 4. So these two numbers are indeed coprime. So we expect it to return the value true. And indeed, that's what we see. Let's try it with a pair which is not coprime. Let's try 3 and 6. They have a common factor of 3. And as you can see, it returns false. So that's good. Our function is working. All right, so now let's actually implement it in the main for loop. Okay, so as I said, we're going to generate 1,000 random pairs of integers. So we're going to start a counter by saying for I in range 1,000, A is random.randint, and I said we choose our lower bound as 1 and our upper bound as 100. So that's one random number. We need to generate another random number. So B is random.randint starting from 1 all the way up to 100. Okay, so this is our pair of random numbers. Now we're going to check if it's coprime. So I'm going to create a boolean called check coprime, and I'm going to say it's equal to is coprime A and B. So it'll return true or false depending on whether these random numbers generated are coprime or not. Now, if they are coprime, right, then we want to actually create a coprimes list up here all the way at the beginning to store the index of any pair of numbers which is coprime. Okay, and we also want a totals list to store all the indices of all the random number pairs that we generate. Okay, so if the two numbers we generated are coprime, we want to add the index of this particular instance in the fault to the coprime list. So we're going to say coprimes list dot append I. Okay. Lastly, we want to add every single instance to the total list. So total list dot append I. So now we can calculate pi. I'm going to set a constant k. I'm going to say it's the length of our coprimes list divided by the length of our total list. So if you recall, this is the constant um, 6 divided by pi squared. So essentially we're calculating the probability that any two random numbers are coprime. So and this ratio works out to be 6 divided by pi squared. So to calculate pi, we need to take 6 divided by k and take the square root of it. And that's how we do that. All right, lastly, we can just print out pi. All right, so here's the big moment. If we run this program, we see that pi is approximately 3.17. Alright guys, there it is. I'm pretty happy with my first attempt at calculating pi, so see you next time.